We can begin with a word of prayer, I suppose. Oh, you already got it? How long I've been talking? Oh, okay. I didn't hear the beep. I was like, what? I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, and just pray that you'd be with us this day, Lord. In your name I pray. Amen. All right, so let's see here. The fundamental theorem of Galois theory. So Isaac has another one of these shirts that's white with like an orange. Ginny's made about 7 of these. They were handed out as party favors for Isaac's birthday Saturday. So like all the kids have these shirts with ties on them. And but Isaac's white with orange one really looks like a Big Lots advertisement. Fundamental. Theorem of Galois theory. So this is Theorem 14 of section 14.2, is it? Thumb and foot, of course. And let's see here. So basically, we have this interplay between subfields, right? E containing F. And subgroups. Let me make it closer. I'm going to try to fit it all in here somehow. Let's see here. Subgroups H of G, right? Given by, so we take E, and it maps to the what? Elements of G fixing E. Do we have a notation for that? Oh yeah, I keep wanting to use the fixed. I forget where I am, you know. So gal K over E. Thank you. And then the other one, the fixed field of H. That H, of course, maps to that. Of course, the fixed field of H is also known as what? Yeah, K upper H. There we go. These are inverses to each other. Indeed, under this correspondence, we have a list of grievances. No. A list of good things. Let's see here. Number 1. It's inclusion reversing. If E1, E2 correspond to H1, H2, respectively, then what? E1 subset of E2, if and only if what? H2 is a subgroup of H1. 2, the degree of K over E equals to the size of H, and the degree of E over F equals to the index of G and H. So you notice that these are different animals. Here we're talking about degree of field extension, right? Here we're talking about number of what? Number of H cosets, right? In G, so group theory versus field theory there. To this and this. Oh, I mean, that's the statement. So it's not if and, it's just, hey, that's true. Okay. 3, you notice that this doesn't assume that this does not assume that H is normal, does it? Oh, you guys. This is a really weird. I mean, I guess that's a possible, tower of fields. It's just not terribly, or it's a possible group lattice. Yeah, that's supposed to be an H. Okay, yeah, sorry about that. Okay, fine. 3, K over E. So enjoy this, guys. This is the last time I'm writing this in here. K over E is always Galois. Always Galois with the Galois group. I guess I already wrote it in my by the advice of Sam over here, right? Well, anyway, that's the Galois extension with the Galois group being H there. Huh. That's a weird, he's got a little picture right here. Do you care to interpret it for me? Right beside that, he has a K, an E, and an H beside it. What does that mean? I personally think this is a typo because it would make sense to me if we did this. See, because that's this statement up here. That says that the degree of K over E is given by H, the size of H. Just an H sitting there, I'm not sure. Well, anyway, but maybe I just don't understand things deeply enough yet. So anyway, possible typo. Possible just me not understanding Galois theory deeply enough yet. I'll leave the, I won't make an official verdict. Okay. 4, E is Galois over, now this is where it starts to get more interesting. E, in fact, I should probably write this over here. Number 4, E Galois over F. So now we're talking about the intermediate field over the base field, okay? E is Galois over F if and only if H is a normal subgroup of G. All right. If this is the case, then the Galois group is isomorphic to the quotient group. Galois group of what? Galois group of E over F is equal to the quotient of G by H. More generally, he says, even if H is not necessarily normal in G, the isomorphisms of E into a fixed algebraic closure of F containing K, which fix F, are in one-to-one correspondence with the cosets sigma H of H and G. All right, let me write that down more generally. The isomorphisms of what? Isomorphisms of E. Where is E? E is in the middle, right? The isomorphisms of E into a fixed algebraic closure of F containing K. I guess we'll use F bar for that. Is that the algebraic closure, isn't it? So F bar containing K, which fix F. So it's the isomorphisms that are doing the fixing, which fix F, are in one-to-one correspondence with the cosets sigma h of h and g. That's right. I mean, you guys remember from the discussion of, what is it, Lagrange's theorem? Proof of Lagrange's theorem, that's given for a finite group, finite subgroup, even when the group is not normal, we still have counting, right? I mean, you still have that the order of the subgroup has to divide the order of the group, and that's essentially, the proof of that essentially just taking the group and chopping it up into cosets, which have to have equal size, even if they don't permit a group structure, right? So this is more of that at play at this level of discussion. Anyway, 5, if E1, E2 corresponds to H1, H2, then what? Oh, intersections. Then E1 intersect E2 corresponds to the, I think this is called the, what's this thing called? H1, H2. It's a subgroup generated by H1 and H2, right? What is that? Is that called the, I'm trying to remember what's the name in group theory for that? If we take two subgroups and look for the group which is generated by taking all of those things together. What's that called? It's not the intersection, right? It's what's the name of this? This is the subgroup which contains H1 and H2. I want to say join, but I'm not sure about that terminology. But yeah, it is definitely the subgroup generated by H1 and H2. You're not wrong about that. So there you go. Likewise.
Yeah, it literally just calls it the group generated by.
Yeah, that's what it says here. I'm just trying to remember if there was another term for it. But this is the composite field, right? E1, E2. So products of all possible things from E1 and E2 corresponds to what? The smallest possible subgroup, which you form from H1 and H2, namely the intersection, right? It's the smallest common subgroup to H1 and H2. And he says, hence, the lattice of subfields of K containing F and the lattice of subgroups of G are dual. The lattice diagram for the one is the lattice diagram for the other turned upside down, right? Now, bits and pieces of this have already been proved, right? For example, we proved this thing about 2 weeks ago, I think at this point. I mean, that's what the first thing we pointed out is the flip-flopping of the fixed fields with respect to the inclusion of the subgroups. So that's old news. The proof of most of this is given on page 575 and other things we've already done. I think, though, what I'd like to do is to focus on the examples here. So let's forge ahead. I want to try to find one which actually has, let's see here. He says Q adjoin root 2 and root 3, or Q adjoin root 3 and row. Extra parenthesis there. Oh, no, there's not. Let's see here. Let's look at, well, I guess the Q adjoin, this one is relatively simple. This extension field and discussing. So that, what are the subfields of that? We had what? We had Q adjoin root 2. We had Q adjoin root 6, thanks. And Q adjoin, what's the other one? Root 3, yeah. And those are all over Q, right? And I think, kind of everything, it's 2's all around, right? 2, 2, 2, 2. These are all degree 2 extensions, right? I'm trying to remember. So to fix, tau, if tau is a automorphism, right, up here, we fix it by doing what? I mean, how do you, if this is a Q fixing automorphism of Q joined root 3 and root 2, I think we pretty much, what do we have to work with there? I think we've gone through this another day, right? It's K4, right? I think we actually did, specifically here, we had like sigma, which did what? Sigma took root 2 to minus root 2, was it? And it fixed root 3. And then we had the tau, which we actually fixed root 2. And we flipped the sign on minus root 3. And then sigma tau, right, changes the sign on both. So basically the automorphism group of Q adjoining square root of 2, square root of 3, I mean over Q, of course, right? That's everything, right? Because we automatically fix the prime subfield. Which most of you know what that is. See here. Sorry, I can't help myself. Anyway, so that has just one sigma tau and sigma tau. Right. And so if I call that would be G, right? In this language, perhaps. To remember how the picture goes then. So we put what? We put 1 up here, and then what's below here? This is the fixed field of what subgroup? Yeah, 1 in tau. This is the fixed field of what subgroup? 1 in sigma tau, right? This is the fixed field of 1 in sigma, right? And, of course, downstairs we have G again. And what's this? There's something else here, right? I mean, the next thing he talks about, not long after this in this section, or has he already talked about it and I forgot? Has he already talked about the Galois conjugates? I think that was back a few pages. I think I neglected to say something in class about it because we talked about it before. He says, let K over F be a Galois extension, the elements alpha of K, alpha and K, the elements sigma alpha for sigma in the Galois group of K over F are called conjugates or Galois conjugates of alpha over F. If E is a subfield of K containing F, the field sigma of E is called the conjugate field of E over F. So we can see conjugate fields at work here. Like, how do you get, how do you get from here to here? I mean, you can get from one to the other by what? Is that right? I'm trying to think here. Well, sorry, I'm getting too carried away. Can you guys tell me anything else to point out here? We're given from the outset what? K over E is Galois, right? So what's K here? What's E? This is the quote-unquote K, right? This is the quote-unquote, well, that's not E. This is E, right? This whole level, these are all E, right? So it says K over E is Galois. Well, yeah, I mean, they're all degree 2, right? So we know any degree 2 extension is Galois. Previous discussions. But then, how about this is F, right? In the language. Is E over F Galois? What is the rule there? You're like, they're degree 2, so they're Galois. I know, but bear with me. I mean, are these normal, excuse me, are these normal subgroups of G? Well, yes, they're, what's their index? They're all index 2, so they're normal. So, I mean, admittedly, this is not really using the fundamental theorem, but it's observing it in play, right? All right, so the next example, of course, is more exciting because I think we actually have a non-normal subgroup in this one. What's that? An abnormal subgroup, yeah. So Q would join the cube root of 2 and rho. And here I believe, again, this was from the start of the section, right? Let me look at just a second here. I gotta find my papers. Here it is. So I think the rho was a third root of unity. Is that right? Here? Yeah. So this is the splitting field of what? X cubed minus 2. I think that's how we first started thinking about it. What have I done? Oh, it doesn't? Yeah. I think it's because it said it earlier. I'm pretty sure this is third root of unity because...
Yeah, because it says that there's a mapping, a map rho to rho squared, and the fact that you can do that would imply that it's a third root of unity.
Yeah, that is true. If well, rho to rho squared would amount to complex conjugation here. Yeah. If it really is the third root of unity.
I think they refer to the examples where they said that it is.
Right. Yeah. Exactly. So Emily is right. If we had a better memory, or if I didn't take 3 weeks to cover this material, you might remember that this is just referring to a few pages back. Okay, so Q would join the cube root of 2. We've got Q would join rho cube root of 2. So these are all the solutions to x cubed minus 2 equal to 0, right? And the complex is these three guys. And then rho squared. Oh, that's unfortunate. Rho squared cube root of. I need a better notation. Cube root of 2. Anyway, you know they're different in your heart. Let's see here. My notation is misleading.
Well, rho to the 23rd is rho squared.
Rho to the 23rd is rho squared. That is very unhelpful.
Except now we have a square root of 2.
Yeah, which is, yeah, all right, well, I'm going to ignore you. Let's see here. But well played. All right, let's see here. Q. So down here, of course, we have the subfield Q would join rho, right? That fixed that subfield, and of course, then down here, well, I should probably make myself more room. Make it a little bit more row. Horrible. Let's see here. All right. So there's your lattice of subfields of the splitting field of x cubed. And then, so to define the automorphism, right? So to define automorphisms, of, let's say here, if tau is an automorphism of this, I need to give this stupid thing a name. What is this called? The big one, K, right? So if we're looking at tau going from K to K, we pretty much just have to do what? We have to say what tau does to, where it sends cube root of 2 to, right? And we also have to say where it sends rho to, right? And those things, as Emily has pointed out, are worked out in detail earlier. Let's see here. Be good for me to remind you. This is example 5 on like page 564 is where all the gory details are for this one. But basically, he looks at sigma, which the sigma one, what it does is it sends root 2 to its third root of unity times root 2, cube root of 2, and it fixes rho. And then also this tau is specifically defined to fix the cube root of 2, but it sends the third root of unity to third root of unity squared, which, by the way, is equal to minus 1 minus rho. There is the cyclotomic polynomial, the n equals 2, the third cyclotomic polynomial at play. Unfortunate wording on my test. Part of the reason I'm giving you guys such a generous reworking is because I kind of set you up for the fail there by calling it the cyclotomic polynomial of degree n. That's self-defeating. It's the cyclotomic polynomial. It's the nth cyclotomic polynomial of degree phi n. Like the third root of unity has a third cyclotomic polynomial that's x squared plus x plus 1, which is, by the way, why this is true. So the second one is the second cyclotomic polynomial is x plus 1. The fourth cyclotomic polynomial is actually x squared plus 1, because it's the product of x plus I and x minus I, which are the primitive. Those are the linear factors corresponding to the primitive roots of unity. So I felt bad about my wording, because I had obviously confused some of you with that, and my bad. So, okay. Anyway, so that defines the that defines sigma and tau, by these rules, and then in page 564 and so forth, he works out the rules. What are the rules? In short, he works out that the Galois group, and we know it's a Galois group. Why? It's funny, he calls it sigma 3 back here, but it's rho. Okay. That's funny. I guess it's that he doesn't want to have the third root of, he doesn't want to have the zeta sub 3 peppered all over the calculation before this, so he swaps the rho out for zeta sub 3 in the concluding couple sentences here, I think. So if you read on page 565, he's got, Galois group of cube root of 2 adjoins zeta 3, but he's been calling zeta 3 rho up to this point, so it's kind of like it's disturbing to me a little bit. Anyway, the Galois group of that over Q, which of course is the full automorphism group because Q is the prime subfield, is exactly the subgroup generated by sigma and tau. Where what? Where sigma cubed equal to tau squared equals to 1 And we have sigma tau is equal to tau sigma squared. You may recognize this, right? So let's see here. You could also do what? You could trade this. This would be equivalent to what? Sigma tau sigma equal to what? Tau, right? So you might recognize this and that from last semester. That's exactly the generators and relations version of S3. So the Galois group of K here is exactly S3. Let's see here. So the corresponding subgroup diagram, we have one upstairs, right? What are my subgroups correspondingly then? Let me say it a different way. This is the fixed subfield of what subgroup? 1 in tau. That's the fixed subfield of what? What fixes 1 in sigma tau? One in sigma squared. Could it be tau sigma squared? I should probably. I'm not sure about that. Maybe I should do tau sigma. I haven't thought it, which is, you know, I gotta be careful which side it's on because otherwise I can write the same thing twice, which would be embarrassing. I mean, what's the rule? If this is the fixed subfield of that, what do I need? I mean, what's a typical element here look like? It looks like A plus B rho cube root of 2, right? Well, is that it? Oh, hold on a second here. That's what? I mean, what? These are degree 3, right? Over Q. So that's not it. It's that plus what? C rho cube root of 2 squared, actually. That's a typical element in here, right? So what would fix that? Tau fixes tau sigma. How about the third one is what? Something of the form rho squared. Cube root of 2, yeah. So what happens when we hit tau sigma on this? Do you say tau sigma is good for the first two? So what happens when sigma hits this? The sigma squared pulls out, right? I mean, the rho squared just filters through it. And then what happens to these guys? Oh, you said it picks up I see what you're saying, rho squared, and then, well, we still have two of those guys. Oh, so those just flow through tau.
Remember the fourth is rho, which maps to rho squared. So
And tau of rho, what happens to tau of rho? Oh, yay. So it's fixed. Anyway, there's obviously some things to calculate here, right? But
although we didn't even need to do that because we just said, well, this is tau rho cube root of 2 squared, and we already know that tau fixes rho cube root of 2. So.
okay, good, yeah. No doubt there. So what's over here? So over here we have the cyclic subgroup generated by sigma, right? And then down here, of course, we have sigma tau. So here you can actually see some things going on, right? Like these, the index of these subgroups is what? These subgroups all have index 3, right? And in fact, they're abnormal, if I'm to use Sam's terminology, which I'm willing to. These are not normal subgroups corresponding to the fact that these are not Galois. These guys are not Galois over Q, right? We've looked at the automorphism group of Q3, of Q adjoining root 3 over 2. We found it was just the identity, in fact, right? These are not Galois. Anyway, on the other hand, this guy, well, that's what? Degree 2, actually. This is a degree 2 extension because this is the zero of the irreducible polynomial, the second cyclotomic polynomial, x squared plus x plus 1, degree 2 extension. Or, if you want to look at it from this way, that is a normal subgroup of S3, excuse me, that is a normal subgroup of S3 because it has index 2. This is a subgroup of order 3, that's an order 6 group. So you need 2 cosets to fill out the group. It's index 2, which is normal. So we start to see the Galois group at play, right? Now there's another example, which I obviously won't be able to cover today, and I probably should just project if I had any common sense. What's the next example he has in 14 point such and so forth? The big one, yeah. Where's that thing? The splitting field of x to the 8th minus 2, right? And it's got a lot to it. Now, we are now to the point, guys, where if you should be able to start reading the PDFs by Conrad and looking at his discussions of Galois groups. You'll find them incredibly useful. He actually gets into more of the mechanics of how you figure out what the fixed field is and how you determine the automorphisms, and which ones you rule out and how that all goes. He has a lot more calculational background in his PDFs if you look at them. So I'll try to pick one of the examples from Conrad and maybe work through it next time, something like that. We are approaching the point where we'll turn the page and look at how to construct the Galois group of sort of like a generic. So this really neat thing coming up is rather than looking at specific polynomials, we look at sort of this generic nth order polynomial and find the Galois group for this generic nth order polynomial, and we'll find out that that generic nth order polynomial has a Galois group of like S of n. Sort of featureless, you know. I mean, that sometimes happens. Here we had, you know, x cubed minus 2. Its Galois group actually was S3. But over here we had a fourth order, actually. That's the splitting field of x squared minus 2 times x squared minus 3 was fourth order. And the Galois group was not S4, right? It was actually what, K4. So the Galois group can be as big as Sn, but it doesn't have to be that big. And that discussion somehow gives the machinery you need to prove that there doesn't exist a quintic formula. It leads to that somehow. So that's kind of where we're going. I'll try to do some more examples of this, though, because I think it's important. Yeah. Thanks, guys. I will soon post the solution, by the way.